This video is for Unit 7 Biomechanics in Sport and Exercise Science and is for 7.2, looking at forces in sports performance and linked to equipment, of course. Specifically, we're looking at B6, the Magnus effect. We're building on the previous video and our understanding of the Bernoulli effect and the impact of different air pressures on different sides of objects. So here's a question for you. If this was a ball and this blue dot here represents the centre of mass of the ball, and I wanted to send this ball away with no spin whatsoever, what would I need to do? How would I create that? What sort of motion would the ball leave and travel in? Conversely, if I did want to create spin, what would I need to do to the ball? How would I need to contact the ball in order to create spin? And what kind of motion is that ball then travelling away in? So let's look at the answers to those. First of all, left-hand side here. This is the ball, there's the centre of mass. This ball is going to be struck left to right, and these blue arrows represent the airflow as the ball goes through the air. So, in order to strike the ball and it to go away without any spin on, I would need to apply a force directly through the centre of mass, and that's called a direct force. So, to send a ball away, I think in football there's something called a knuckleball, which more or less does this. The ball is struck right in the middle, and that's called a direct force right through the centre of mass, and it should travel and leave in a fairly linear motion way, i.e. straight without any rotation or spin. So, if a direct force is applied through the centre of mass, it means there's no spin on the object, there's no pressure differences, so this air will flow around the top and will flow around the bottom at the same velocity and carry on behind. There'll be the same air pressure above as below. So air velocity and air pressure around the sides of the ball will be equal because the ball is not spinning. Knuckleballs, I believe, are effective because they're a little bit unpredictable. They kind of wobble rather than spin sometimes in the air. So the second thing was, how do I create spin then? So in this case, on the right-hand side, what I need to do is apply a force, not through the centre of mass, but somewhere outside of the centre of mass. And it could be over the top, could be the side, could be the left, could be the right. But importantly, I apply a force not through the centre of mass. And this type of force is called an eccentric force. And what that means is that the ball would, so if I apply a force beneath this ball, beneath the centre of mass, it would spin anti-clockwise. And instead of having linear motion straight line, what we do is we create angular motion or rotation of that ball, and the ball starts spinning. And that's half the story actually, because now we need to look at airflow going above and below the ball, and this is where the Magnus effect comes into play. So we've got a ball that's spinning in the direction of the dark blue arrows. We've got airflow that's coming towards the ball, or the ball's going through the air. Now, as the ball is spinning this way, the airflow the ball is travelling through kind of comes in and hits the rotating airflow, this boundary layer of air that's coming around with the ball, especially on something like tennis balls where it's got a fluffy surface. That material grabs hold of the air, has a boundary layer, and we've got a conflict. We've got air coming around this way, and we've got air coming this way. So the velocity of the air here beneath the ball is slowed down. It's basically blocked and slowed down by the oncoming pale blue airflow. So velocity is low, airflow below is low, which means that the pressure here is relatively high. So air pressure is high because the airflow is slow. On the top side of the ball, remember the ball is spinning this way, we've got the airflow of the ball travelling the same direction as the airflow approaching the ball. And as you might imagine, it's almost like it spins it round even faster, so it comes round and joins in. So we've got a high velocity airflow on top, which means there's a relatively low air pressure. So we've got slow or low velocity, high pressure below, high velocity, low air pressure above. We've got a high pressure to a low pressure, and this ball will probably be lofted or have additional lift force and sit in the air for a bit longer. So if this was a lob and I did a slice shot, even in table tennis the same would apply, or tennis, if you want to lob somebody, yes, you can do a topspin lob, but you can also do a backspin lob. So if this was a backspin shot, the ball would go really high and lob above the person and plop down in near the back of the court. So we've concluded that we've now got low air velocity beneath and high air pressure, and we've got high air velocity and low air pressure above. So we've got this high pressure to low pressure where we get a upward lift force created by the spin on this ball. So an eccentric force applied not through the centre of mass means the ball spins, and the ball spinning means we have this influence on the air velocity going around the ball, and therefore the air pressure on either side of the ball, which causes a high to low pressure gradient, and the ball is lofted. So in a nutshell, that is the Magnus effect. It's basically Bernoulli applied to spinning objects like, most cases balls, footballs, basketballs, tennis balls, table tennis balls. So a lot of our racket sports like table tennis and tennis, cricket, bowling and cricket, it really uses spin to influence the flight path or the trajectory of the ball. And we create spin on those balls to change, the route with which the ball takes and try and be tactical with our techniques. So this extra force that redirects the flight path of the ball is called the Magnus force or the Magnus effect. It's an additional force. It's a bit like lift. Lift is an additional force. The magnet force is an additional force applied to balls or spherical objects by this ability to make them spin. Here's some examples of, for example, in tennis, how hitting a topspin shot, the ball is rotating clockwise. What we get is a loopy trajectory over the net, and then it makes contact with the ground and it spins off away and it bounces up high. No spin is fairly neutral. If you do a slice shot, so the ball is spinning anti-clockwise, it stays very snug to the net and doesn't pop up very much. So a different kind of outcome and flight path. So take your time, look through this example. We've got a tennis player striking the ball, hitting it with topspin, hitting it over the top of the ball. So that eccentric force is above the centre of mass, creating spin in this direction, which creates low velocity flow because the airflow here is banging into the oncoming airflow and slowing it down. We've got low velocity, high pressure. The air coming around here, this boundary layer of air, is getting accelerated on this side of the ball. So we've got high velocity, low pressure. High to low, the Magnus force works high to low downwards. So that ball will pop down, spin. And here's an equivalent example of a backspin or a slice shot. So the player strikes the ball beneath the centre of mass, applies an eccentric force down there. The ball is spinning clockwise, and you can see this side, the velocity is low, pressure is high. This side, the airflow is being accelerated. It's in the same direction as the oncoming airflow. So we've got high velocity, low pressure, low to high. The Magnus force is upward. Basketball shooting is another example. Typically when you shoot, you flick your fingers underneath the ball and you create this backspin on the ball, and exactly the same principle is applied. We get this Magnus force giving it a little bit more arc, a little bit more flight, because when shooting, a high loopy shot is better than a flat shot. It can't magic into the basket, so you've got to shoot upwards and get some lift, get some Magnus force on the ball to give it a nice high flight. So many of you may play football and have tried to put spin on the ball to make it swerve to the left, to the right, or loft the ball, struck it at the bottom of the ball to give it extra height. I suppose topspin isn't really as applicable in football as it is in our racket sports. But here's a little explanation of how that spin, that eccentric force applied to a ball, creates spin, creates a curve.
Carlos kicked the ball, he gave it direction and velocity. But what force made the ball swerve and score one of the most magnificent goals in the history of the sport? The trick was in the spin. Carlos placed his kick at the lower right corner of the ball, sending it high and to the right, but also rotating around its axis. The ball started its flight in an apparently direct route, with air flowing on both sides and slowing it down. On one side, the air moved in the opposite direction to the ball's spin, causing increased pressure, while on the other side, the air moved in the same direction as the spin, creating an area.
So I just want to pause the video there because this shows the ball is spinning this way. We've got the air flow of the ball, the circulating air boundary layer of the ball, crashing into this orange airflow, creating a low velocity airflow around it, and therefore high pressure. The airflow this side going the same direction as the oncoming airflow, creating a high velocity airflow and therefore a low pressure, exactly what we've been looking at before.
Lower pressure. That difference made the ball curve towards the lower pressure zone. This phenomenon is called the Magnus effect.
So, we spin the ball in all sorts of directions in football, typically left to right, right to left. Sometimes we strike the ball underneath, and it's all to do with this Magnus effect, that due to the spinning ball, we create a pressure differential high to low, and the ball will go off in that trajectory towards the low, from high to low. Again, here's just some images that indicate the side spins, the sort of right to left, left to right spin that you can generate. Golf is another very typical example of intentional backspin. So we have golf clubs that are designed to really exaggerate how much backspin we can get on a ball. And with the backspin, what we tend to get is lift as a force. So we create spin to create the Magnus force upwards. Sometimes when we hit it, we'd hit a hook shot or a slice shot. We don't really want to. We send the ball off to the right. That's gone from high to low. We strike it on the left, so and it veers off to the right, or vice versa. We hit it too much on the right and it veers off to the left. So often we intend to do a slice shot, a backspin shot. Sometimes we do a side spin shot unintentionally. Last example, table tennis. Probably a brilliant example of how extreme spin gets put on the ball, deviating its flight path and making it veer left and right. Have a little look at these amazing table tennis rallies and look for the spins. There's all sorts of different directional spins.
Swipes the ball just... Shot block, lob comes down. This time it's on. Forehand counterattack. Back to the lobbing game. Way off in the backhand corner. Inside out, the racket's gone. The ball's on the table. When have you ever seen that happen? Oh my goodness, just speechless. Xu Xin the pressure to make this shot. Crazy to see.
There we have it. So that's the Magnus effect. We've looked at the application of this Bernoulli principle to spinning objects. Broadly speaking, it's the balls that we use in our sports, and we manipulate the airflow around them by the spin, which influences the air pressure differential, which basically makes the ball deviate, swerve one way or the other.